Today I've been invited to come in and Chris and I talked about potential topics. I was just saying that I've been making presentations around the country at different universities, probably 15 times in the last 6 or 8 years. And so constantly changing it. This is not going to be a super technical presentation. But I'm going to cover some concepts and I'm going to talk about some strategies that we use and then have some case studies. I would be very happy if somebody wants to ask a question, and we're going to try to use the raising the hand thing on the participants, except I can't see that. So that's probably not going to work. So if you have a question, just yell. That's going to be the best way to do it, I think. Now, if I can get this thing to advance, there we go. I'm going to do two quick commercials, which you guys just got. One of them is because of it's EERI, and there's a program there called the Friedman Family Visiting Professionals Program, and that's one of the reasons that I've been making presentations around the country. It's a grant from the Friedman family, and they allow professionals to go all over the country. I was actually at Tech 2 years ago by virtue of that program. So EERI is a wonderful organization. I'm supposed to be doing like a 12-page commercial, but I just cut it down to 1 page. But what my big message regarding EERI and SEI both is, you know, any students that are involved while in school, there's a tremendous opportunity to stay a member of those organizations as you become a young professional. There's big discounts and membership fees and everything else. So please consider doing that. SEI, the other commercial, it's the largest. It's over 30,000 members of the 9 institutes. It hosts a structures congress in the spring. It's going to be virtual, obviously, next spring. There's 5 divisions. There's over 100 committees. SEI is responsible for writing the major sections of the building code, ASCE 7, which is the loads. There's lots of opportunities to get involved. And I'm proud to say that 2 years ago, when I was president of SEI, we joined up with NCSEA and CASE to write a joint vision for structural engineering. So I am done with SEI on the board now. I just dropped off the board as past president, and I am president-elect of EERI. So obviously both organizations are near and dear to me. Today we're going to just do an introduction. Then I'm going to talk a little bit about learning from earthquakes, then give you some case studies, and then at the end talk a little bit about students' careers and the future of structural engineering. My career is I graduated from Tech in 1980. I followed a girl to California, ended up marrying her, and we're still married. Went to work for Degenkolb Engineers in San Francisco. And then in the meantime, while working full-time, I got my master's at San Jose State, which was interesting with the commute. Then after the Northridge earthquake, I moved to LA to start up the Degenkolb LA office in '95. And then while working on the Hotel Del Coronado, I'm gonna do my cursor. Hotel Del Coronado, which is this center project right there, we opened up another office in San Diego. So I was running both of those offices. Then in 2001, I left and started my own firm, Structural Focus. And we have a staff of 25 people now. Did about $4.5 million in revenue last year, and hopefully we'll be somewhere close to that this year. And these are just some of my Degenkolb projects that I worked on in my early career. Our practice at Structural Focus is kind of all over the board. We do commercial and office spaces, a lot of evaluation and strengthening of existing buildings, higher ed, historic buildings, hotels, laboratories, a lot of work for the film studios, which is very interesting. Some very large custom residential kind of projects, and then we do some back to business programs, which are post-earthquake or post-disaster inspection programs for owners. And here's a collection of some of our projects we've done over the years. So structural engineers, that's enough about me. Structural engineers, I always like to throw this slide in there because I appreciate the fact that Wikipedia has this second sentence. You know, the first one is kind of what you would expect. We inspect, analyze, design, plan, and research structural components and structural systems. The second one, though, is pretty interesting that it's in there, that we take into account mainly technical, economic, and environmental concerns, but also consider aesthetic and social factors. And I think that's really great that that is listed in our description. Structural focus, our mission is we exist to do projects that we can be proud of and proud of how we do them. My point is that structural engineers, it's more than just analyzing and designing a building, its connections. There's also other considerations, sustainability, public safety, aesthetics, community resilience, preservation of historic structures, and then obviously the client's needs. I mean, we're working for clients and we have to pay attention to what their needs are. We need to understand not only them, but the impact that we have on the natural and the built environment. So 5 things that we do at Structural Focus that we like to emphasize is we like to think like our clients. We want to put ourselves in their shoes to understand what their needs are. We explain and use performance objectives whenever possible. We try to reuse buildings. We're not inclined when people call us and say, I need you to look at this building and tell me that I can tear it down. We'd rather save a building than tear it down. We try to communicate clearly, and we like to design elegantly and authentically is the way I put it. And a lot of that maybe will come out as we talk. Learning from earthquakes. I grew up in Richmond, and so didn't know what an earthquake was pretty much. Moved to California and found out that I knew nothing about the main driver of structural engineering in California, and that's earthquakes. Luckily, though, I went to work for Degenkolb, and Henry Degenkolb was kind of the original earthquake chaser. He felt that the real life scenes after an earthquake were the best classroom for structural engineers to figure out how to design and retrofit for earthquakes. So we went out lots of times looking at earthquake damage. And some of the times we're looking for the known deficiencies, we're confirming deficiencies, such as the soft stories in the tuck under parking in Northridge. This is a resort hotel in Costa Rica that I went to back in 91 or 92, where the short column effect took it down. It basically collapsed the building. We also have surprises that we did not expect, the structural engineering world. There was a brand new hospital in San Fernando that was hit by the earthquake in 1971, and it destroyed it because of the non-ductile detailing that's in the columns. And then there was, even in Northridge, we thought, and going into the Northridge earthquake, that steel moment frame systems were the best there is, that they were far superior to any other system out there. And then when we first started hearing reports of damage, we couldn't believe it. Turns out that it was a very significant problem. And then obviously we need to look for key things, the vulnerable building types that are out there. There's the unreinforced masonry buildings. On the left there is the Napa earthquake 2014. That building had actually been retrofitted to the minimal standard in the state, and it still had obviously a very significant problem with that front cupola. The anchors, there were epoxy anchors, and they just pulled right out of the masonry. And then the one on the right is in Kalinga, 1983. That one had not been retrofitted at all. That's a very rural community, and obviously it was heavily damaged.
Excuse me.
Yeah.
The last slide, the one in the Napa, was retrofitted when the earthquake hits it, or after?
This one?
Yeah, this one, yeah.
Yeah, that one had been retrofitted to the minimal standards. There were roof to wall anchors. That's obviously what you look for. And if you zoom in on that area up there at the very top corner, you can see the anchors just swinging free, that the brick had fallen apart, and the brick just crumbled around them down here. They used adhesive anchors, which are not going to work as well when you have weak masonry than if you were to use rosettes. If you put big plate washers on the outside, at least you got some bearing, and it's going to try to confine the masonry so it just doesn't dissolve, is basically what happened. So good question. Also, the vulnerable building types, some more of the soft story buildings in Northridge. There's a lot of these. And then even in the Loma Prieta earthquake in 1989 in San Francisco, these are older buildings, very Victorian. Most of these are built in the teens and the 20s. And they're all wood frame. There's no plywood or anything in there. And literally the blocks were all leaning, and then the end building would just collapse because they were all leaning on each other. Where these buildings were all built in, 60s, 70s, maybe some 50s. They didn't have plywood either, and they all had parking underneath them. So they're a big problem. That's where there were more deaths under an apartment building like that in Northridge than any other structure. So obviously this graph was an attempt by me to show how building codes, or at least seismic building codes, have evolved. The first one was right after the Long Beach earthquake in 1933. There was all kinds of laws passed, and the building code attempted to address earthquakes. But every time there is an earthquake, there's lessons that are going to be learned, and those lessons eventually end up being developed, investigated, and confirmed and added to the building code. So it's constantly evolving. And I put a circle around these two recent ones. San Francisco passed a soft story ordinance where there was a mandatory law to go and retrofit their soft story buildings. And LA did a very similar thing in 2015, but it also included older concrete buildings built before 1980. They consider as non-ductily reinforced. And those buildings have to be retrofitted within 25 years of their notification. So by 2040, the idea is that those 1,500 concrete buildings will all have been retrofitted or torn down. That's their choice. So strategies. We do a lot of work with existing buildings, and there's different ways you can retrofit a building. And I like to think of it kind of as three different paths. And we'll look at all these options. But one of them is to add new strengthening and rigidity to protect the brittle material. So that's when you add shear walls or braces or things like that, that basically just change the dynamics of the building and protect those. It stops the rotation, it stops the significant drift. And so it actually increases the accelerations, but it's a way to protect a lot of the elements in the building. Another way to do it is to actually supplement the existing and by improving the connections or increasing ductility. So you're not really trying to change the stiffness of the building, you're just trying to toughen it up and hold it together. So that's the kind of the strategy number two. And then number three, which is usually the more expensive version, is you modify the overall dynamic response by using base isolation or dampers or something like that. The idea with those, if you're starting from scratch there, it's not as much of a cost premium if it's a new building. But if you're retrofitting, you have to go, if you're going to base isolate it, for instance, you have to go underneath the building, dig out room underneath and shore it up, and then bring the base isolators into the basement and connect it all to the foundation. Theoretically, by doing that though, then you don't have to do a lot of seismic strengthening in the upper stories, everything above the foundation level. So that's where, if it's a very brittle, historic landmark building, then that sometimes is the best solution. And there's been several city halls, San Francisco City Hall, Oakland City Hall, Los Angeles City Hall. There's been many of those kinds of buildings that have been base isolated because they felt that was, Pasadena City Hall is another one. They felt that was the most economical and the best protection for that particular building, but it is expensive to do. So a little bit more about strategy. If you think about it, if you're an owner and you have an historic kind of landmark building and you want that building, what you have to find out though is whether that building is a good investment. You might like the historic architecture, but it needs to be marketable. You need to be able to make money on that building. So they'll ask all the experts, they'll ask the realtor, can we actually, does this building have value? Is it marketable? They'll ask the architect, can this building be usable? You know, is it functional? Is it got the right space? It's got enough light, all the things that a tenant or a user might want. They ask the mechanical, electrical, and plumbing consultant, can it be efficient, you know, with all the energy costs and everything nowadays? So they want to know whether they actually can make this have efficient systems. But in California, what's interesting is many times they'll come to us and they'll say, can it be safe? And sometimes they'll come to us and they'll go, can it be safe? And sometimes they'll go, can it be safe? And they have an end goal, and we often are the deal breaker because the seismic retrofit cost is often the most expensive part of the project. And nobody wants to mess around with life safety. It's always, you know, if you talk about it being unsafe, then everybody runs away. So it's an interesting place for us. And I think in some ways, structural engineers in California are lucky because we have a pretty big voice at the table because of earthquakes. And that to me sometimes is an advantage. So here's some case studies. The first one is the Wilshire Boulevard Temple. It's a 1926 steel frame encased in concrete. It's on the National Register. And we got a call one day that the housekeeping people kept finding plaster chips on the carpet in the sanctuary. And they didn't know where they were coming from. So we got some scaffolding out and started doing some inspections, and we found that the dome, the inner side of the dome, which is plaster, was beginning to chip away around the perimeter. And our theory was that the whole thing was shifting within the concrete dome. There's a concrete dome and then there's a plaster dome. And it was moving around, and where it was hitting around the edges, it had already been weakened somewhat by temperature variations over the years. And it was doing a little bit of pounding against the concrete. So they asked us to do an evaluation of the building. And when we did a computer model, as you can see, the output there with all the blue, that's the overstressed areas that were identified per the analysis. What the issue is the walls that surround the sanctuary, which are the octagonal walls, kind of that wall in the four corners, they're concrete there, but then they stop at that lower roof level. They don't continue. And so what happens is all the stresses have to be chased out the rest of the structure. They don't continue down that wall to the foundation. So at first we did a scheme that basically we were just strengthening all the blue areas. We were going to complete that load path, make it strong enough that it could go all the way down. But that was a very, very disruptive scheme and expensive. So we went back and looked at it, and I made a brave proposal to them that maybe we should bite the bullet and continue these shear walls down through the building. It turns out that those octagonal walls in the sanctuary are basically hollow walls. They're plaster on both sides. There was a big void behind the plaster. Unfortunately, the plaster was a very historic fabric, and it scared them to do that, but they realized that that was a better scheme. So I like to say that we addressed the cause, not just the effects in this particular building. To do the work, they had to make a choice. They had to either choose, you know, you got two faces of the wall. There's the plaster side on the hallway, basically the corridor outside of the sanctuary, and then there's the plaster on the inside, which had a mural on it and some other stuff. So we finally agreed to pull the plaster off of the less significant side and go in and build some studs against the plaster on the inside, and then put some waterproofing on that surface, and then put the rebar in, and then shoot shotcrete against that waterproofing to embed that rebar. And that's how we created concrete shear walls. And it made a big difference. It was a lot simpler project at that point. They did work on all around the perimeter, just repairing the concrete. They also built a complete forest of scaffolding in the sanctuary to get up to the ceiling, to restore the ceiling. So they went back, the artists went back and restored all the plaster and the painting. And then this is one of those low roof areas where we still needed to do some strengthening of the diaphragm. So we used an FRP product, a fiber reinforced polymer product. And I don't know if you guys have talked about that, but basically you go to the substrate, clean it all off, you paint some epoxy on there, and then lay out the FRP mesh. And that provides a lot of shear strength. It doesn't change the stiffness, but it increases the shear strength. And so we're able to use that on the roof diaphragm. We rebuilt the rose window. That was an unreinforced heavy stone. It's about 20 feet diameter, and it's right over the main lobby. We were nervous that if there was an earthquake, it was very heavy. It would fall out into the narthex and come crashing through the roof. So we cut it apart and inserted rebar in it and put it back together. So it's all the original parts, but it's got rebar in it now, so it's heavily reinforced. And then the ceiling I was talking about, this is the ceiling before. It's kind of dirty. This is a ladder that's going up between above the plaster dome and below the concrete dome. There's the plaster dome. You can see the curve of the dome. It's supported by hanger wires. There was not much lateral bracing in here, so we added a lot of diagonal bracing. And there's the connections between the red iron and the black iron, which the plaster is it's cast against. Those those globs right there are just fibers which are globbed with plaster around them. That's how they did a lot of their stabilization back in those days. So that's the final product on the interior. It's a beautiful, beautiful space. It's the largest dome in LA. So it's really something. And that whole church now has come back to life and reinvigorated the neighborhood. It's really an amazing project. Next one is the Proper Hotel. This was an old medical professional building in Santa Monica. It's about 7 blocks from the beach. It's a designated historical building, again, built in 1926. It's got very thin concrete walls. They're 6 to 8 inches thick around the perimeter of the building. 8 stories tall. It's irregular in plan with some vertical offsets at the second floor line. I'll show you that in a minute. It's part of a larger project to build a brand new hotel, a very large hotel with 3 subterranean levels immediately adjacent to the structure. This will become, or has become, part of that new hotel complex. There was significant damage during the Northridge earthquake in '94. The repairs and the retrofit were very poorly done, and the building actually was not in very good shape at all. This is a plan view showing the Y shape of the upper stories, and then the first story basically was a square. So you can see there's this offset at the corner there. So that caused a lot of problems when we did the analysis. That irregularity caused a lot of stress concentrations. I don't know how well you can see it, but there's a lot of cracking and damage to this concrete wall here. When you get up into here, there's a whole lot of damage up in there. And then this is the interior after the plaster has been taken away. This is a window, and I don't know how well you can see that, but there's significant cracks and spalling in that concrete wall there. That was really in poor shape. It actually was kind of scary once we uncovered all the cracks and saw how bad the building was. It was much worse than we thought it was. So one of the things that I just wanted to point out about this project is a lot of times we have to do what's called a mitigation plan when we go in to do a retrofit. And this is just the beginning of the mitigation plan. It's part of the planning approval from the city. They require that. In this case, they required us to go in and do a complete video of all the surfaces in the building before any construction started. So they knew what cracks were there in case there was any claims of damage due to the adjacent construction and the vibrations. They had vibration monitoring. If the vibrations got stronger than the limit, they had to stop work immediately and figure out what they were doing wrong. We were required to inspect the building every month during construction. But all of this is to make sure that the building survived the construction next door. And we've done a lot of this kind of work where historic buildings or very nice buildings are immediately adjacent to construction. And the best thing you can do is go out there and get the original condition so you have a baseline, because humans always think cracks are always getting bigger, and they aren't necessarily getting bigger. So you need to know exactly what you're starting with, and then when you go back and check it later, you've got something to work with. So this building also had a very open, soft story at the ground floor. You can see once we pulled all the glass out and all the finishes and everything, we're down to the bare structure here. There's one wall right there, and that's it. The rest was all non-ductile, reinforced concrete columns, no steel frame. So part of the work we did was, it's hard to explain exactly where this is, but that's a big steel plate bolted to the wall, and there's some of the bolts that are coming out. This is to help drag some of the loads at that second floor level where the Y shape comes down on top of the square. This is to try to transfer those loads back into the shear walls that we had added into the building in that bottom story. This is some more use of FRP that I talked about at Wilshire Boulevard Temple. This is a much more conventional use where we wrap a column, and by doing this, we provide the confinement that we would need now for code, but back then they might use number 2 wires at 5 inches on center, or number 3s at 8 inches on center. It's no way that it's going to be strong enough to confine the concrete core. And so by adding this FRP around it, that does a very, very good job of confining those cores and adding a lot of ductility to the columns. In this case, this is used, that's FRP along there, and there's FRP along there. And both of those are used not only for vertical floor strengthening, but also for collectors, for dragging loads, again, from one area of the diaphragm over to a shear wall. So we've used FRP quite a bit. It's expensive, but architecturally it works really well because it doesn't really add much thickness to the section. You can imagine one option for this column, for example, would be to wrap it with new rebar and then cast an extra couple of inches of concrete all the way around it. So that column would grow by at least 4 inches, and that doesn't always work architecturally. So FRP is a good solution to that. And then in addition to that, we've used it on the concrete shear walls in this particular building. These were very thin concrete walls. They went through, they patched all the cracks first, had prepared the surface, and then put FRP on the surface of the walls. They'll go back now and just put sheetrock over this, so you won't even, again, it won't increase any thickness to the wall, but it will increase the strength, and some of the ductility. It does not increase the rigidity of the walls per se, any measurable amount anyway. So there's the almost done. You see the construction fences up. That's the new hotel, which is very different from the historic building, but you can see this has all been cleaned up and it's actually back to a landmark again. The next project is 9300 Wilshire. How am I doing time-wise? I think I'm okay. This is, believe it or not, is an historic designated building in Beverly Hills, 1962. So now they're considering buildings in the 60s, and they're even getting into the 70s now as historic. This is all concrete construction, but it's not, in 1962, obviously it does not have the ductile detailing that we would like to see in it. It needed to be updated to make it marketable for offices. It was getting really tired. And there were some very strict restrictions on the historical restrictions on the exterior changes that we could make, mostly related to these columns along the street. They did not want to change any of the appearance of that. So the sellers had done, cut off my title. The sellers had an engineer take a look at this, and he proposed a retrofit scheme that would enlarge, these are the columns out here, that would have enlarged those columns by encasing them in concrete, like I just described we could have done at the other building. Then he was going to put a shear wall here and some shear walls along this line here. And that was his scheme. And they, unfortunately, they based a budget on that scheme. When they sold the building to our client, we looked at that and knew that they were not going to be allowed to change those columns on the street side. So we tried to come up with a scheme that would not change those columns. And our first thoughts were, again, we'd do the shear walls here. We needed a shear wall here. We found out that he had missed. We were going to wrap these columns back here with FRP. And then we proposed a shear wall right here next to the elevator core. And by doing that, we felt like we had taken enough, we'd added enough stiffness near to the front of the building to relieve the torsional problems that we were having. And then that way we could get away with just doing a very careful wrapping of these columns out front, because we had greatly reduced the drift in the building. And therefore we weren't causing the problems with those columns that it was having before. We finally settled on a scheme that was, because that shear wall that I had proposed back here was very expensive, because you would had to work in the elevator shafts. We looked at putting it here, we looked at putting it there, we looked at putting it there. And then we proposed, well, why don't we do a massive 2-column, 2-story tall moment frame right here. And obviously this is the lobby. And so by doing that, we're putting this 4-foot square concrete column right down through the middle of their lobby, but we're saving a lot of money, and they liked that idea. So that's what we ended up doing, is taking that shear wall that was going to be here, turning it into a very large moment frame, 2-column moment frame. We still are going to wrap the columns on the front, and the rest of the scheme, we ended up putting a moment frame back here also instead of a wall. But that ended up being the final scheme. We had done an analysis. We played around with lots of different ideas. So that's what we ended up with. Basically, the FRP, all the columns still needed to get wrapped with FRP, which is disruptive, but it's still, in the end, it's a better architectural solution. We ended up infilling some window openings. We put the new moment frame in. We put the moment frame, we put a concrete below a discontinuous shear wall in the back, which the other engineer had missed. And we were able to avoid changing those historically sensitive elements. So that made the project doable. This is a rendering of what it's going to look like. There's one of my big, massive columns right there in the lobby. So the architect at first, said, I don't want that, but then they got used to it, so they're okay. Then my final case study, once again, is a concrete building. It's called the Masonic Temple. It's in Glendale. It was built, I believe, in the 19-teens. I forgot to write the date down. It's a very prominent location in the city of Glendale. There's a big commercial development across the street from it, but it's been sitting empty for decades. It's an 8-story tall building. It was a landmark building and hardly had any original construction documents, which obviously makes it difficult. The owner developer of the development across the street has a lot of political power, and he actually went to his fraternity brother, who is the head guy at CBRE, and convinced him that it would be a great office for CBRE. So that's what they put the deal together. It's a very demanding client and a ridiculous schedule. We started design on May 1st, and they moved in on January 1. So we designed it and built it in 8 months. Typically, we wouldn't even design it that fast. So it was very difficult. Again, a non-ductile concrete building with a lot of planned torsional areas, a really cool space. This is the top floor of the building. That's the CBRE guy. That's the developer guy trying to convince him to do it. So really cool when you walk in here. The building had been previously gutted by other people trying to figure out what to do. This is again that truss system on the top floor. This is actually a hanging mezzanine. It's hung from the floor above. Again, this is part of the original structure. So we performed a detailed seismic analysis. The biggest problem in this building was torsion, that it really wanted to twist. There were some discontinuous walls. It was very soft in the back. And we ended up closing some windows and adding some new windows. And by playing that game, we were able to make the system a lot more symmetrical and minimize the torsion. And so it was an interesting game with the owner and with the architect to do that. And at first they thought we were crazy because we were suggesting putting in more windows, but they liked it and they didn't argue with us. And we eventually got it so we could get a very symmetrical response out of it. We ended up strengthening some shear walls. We added a few new shear walls, especially under some discontinuous ones. We had to connect the mezzanines. Most of the mezzanines weren't really connected to the structure for lateral, so there's no place for those loads to go. And then we added a few mezzanines also. So there's that hanging mezzanine I pointed out before. This didn't really change structurally, but you can see the new look. And everybody always thinks that's a new brace that we put in the building. This is the top story. Architect standing there looking at what in the world have I done. This is the construction, and that's what it looks like now. So we built a mezzanine all around that space. And this is CBRE uses this as hoteling space. There's no fixed offices. You come in and choose your spot for the day and move around. But it's a beautiful space. So that's the finished product right there. You can see the light hits the board form concrete, which really makes it cool. So those are my case studies. Anybody have any questions before I go? I just got a few more slides.
Yeah, I just want to ask something about these retrofitting projects that you showed. I guess I saw a combination of using FRPs and shear walls and different techniques, or resolving these discontinuities in the buildings. I'm curious, how do you I think there are multiple schemes to retrofit that is proposed in the initial sessions, and then you finally choose one of them, right? Yeah. And I think there were different drivers. In your experience, what is kind of the most significant driver to choose any of these schemes for a specific project on average?
Well, money is always, if not the top consideration, it's one of the top considerations, obviously. Schedule is obviously one, but then the other ones are, what's it doing to the building? Is it still going to be a usable building? And if it's a designated historic building, you have those restrictions too. So you can't even, 9300 Wilshire, we couldn't touch those columns. We couldn't change those columns. So in some ways, I like retrofitting buildings more because it's a puzzle. You've got this thing and you've got these rules, and you have to figure out that puzzle. You have to do some detective work because you got to figure out what the materials are if you don't have all the drawings. And then you've got to sit down and work with the team about what's the best solution to that puzzle with all those considerations. So it makes it, for me, it's very interesting in some ways. I mean, I love doing new design also, but new design, you think about it, you're starting with a relatively blank canvas, where retrofitting, you've already got issues that you're trying to deal with. So in some ways, to me, it's more fun.
Thank you.
Yeah. Anybody got any other questions about the case studies?
I have two questions.
Sure.
First, you kind of mentioned it in one of the last case studies, but I'm curious. I'm a geotech, and I've found in some of these retrofit jobs, one of the hardest things for us is lack of accurate as-built or lack of as-built plans at all. And for us, we really have to go in and dig up to see what's going on. I imagine that it's maybe a little bit easier for structures if you can see them, but I imagine for a lot of these historical buildings, they don't really want you to go in and see what's behind their walls. So I'm curious if you have any specific techniques that you usually use to get a good idea of the structural systems in those cases.
Yeah, I mean, we'll do ground penetrating radar to try to find the rebar and identify what the rebar is. We'll take x-rays. We'll take cores just to test the compression strength. Sometimes we'll try to get rebar samples. You know, these non-ductile concrete, these 1,500 concrete buildings out there that need to be retrofitted. I keep telling the material testing guys, I said, you need to come up with some magical method that you can tell us what all the rebars are in those buildings, because probably maybe a third of them we have drawings, maybe at the most. So that's a big effort, you know, and owners, a lot of times when they first talk to us about those buildings, they don't realize how much money they're about to spend just trying to figure out what they have, until we point it out to them. We say, you know, if you can find the drawings, you're going to save yourself $50,000, $100,000. And they were like, oh, okay, I'll get serious about finding the drawings. But we'll do potholes for the foundations, same as you. You know, we need to know where it is if we're going to undermine the foundation, for instance. If we want to strengthen the foundations, we need to know how deep they are and how wide they are. And then you guys need to look at the soil down there at that level. And there's a lot of detective work that has to happen. So I don't know if that helped, if that answered your question, but yeah, you're right. That's a big deal.
Thank you. My second question is, I'm curious if you have ever worked with any structural health monitoring systems that have been put in place on any of these buildings, and if so, how any sort of data collected by those systems has matched up with your models.
We are just starting to do that. We've actually got an agreement with one supplier that we just signed a few months ago for two reasons. Number one is to help us with, well, to help our clients. And if we can get any data out of that to see if it matches what we expected. But also, as I said, we put these post-disaster inspection programs together, and that can help us with that too, because if they already have the monitors in the building, when there's an event, we immediately know how much shaking occurred, not only at the site, but also the building. And if the building is shaking, is moving more than we expected, because we've already done an analysis of the building in advance, we immediately know if we have serious issues or not. So we're just beginning to get into that. It's a really interesting idea, and it's not nearly as expensive nowadays as it used to be. It used to cost a fortune. I mean, to instrument a building, I don't know, 5 years ago, it was something like $100,000. Now it's just a few $1,000s. So it's really advanced quite a bit.
Interesting. Thank you.
Mm-hmm. Any other questions? Have we still got some students on the line, I hope? I can't see my participants list.
Oh yeah, no, we actually ended up getting more joining.
Good, good. So this last part, just a few minutes, I just wanted to talk about students, you know, path moving forward. The thing that I didn't realize when I was in school is that it's more than just doing calculations. You know, I wasn't the greatest student in the world. But there's a lot to being a successful structural engineering consultant, because you have to do calculations, you have to do analysis, but you also have to be good at doing conceptualizing, you know, sitting with that team at the beginning of the project and trying to figure out how you're going to retrofit a building, for example. You have to have some creative thinking and some vision for what you're trying to do. Imagination and creativity I just talked about. We have to coordinate a lot, and the state of the industry right now, in my mind, the architects somehow have taken over as the design professionals. Generally, and traditionally, the engineers all work for the architect, but they're not any better trained at coordination and management than any of the engineers are. In fact, we tend to think a little bit more about coordination, I think, than they do. So we end up doing a lot more coordination than I ever imagined. We also have to be good at negotiating, whether that's negotiating a contract or negotiating a scheme, a design. We have to be good at communications, writing and speaking, so you can understand, so the client can understand what you're trying to explain to them and they can make the right informed decision. We have to be good with people. Nobody likes to work with a jerk. And we also have to, by the way, we're running a business. So it's there's a lot more skills than just the math skills that you can learn. I want to point out to the students that we really could use your help in elevating our profession. As I said before, we're the deal breaker a lot of times, and we need to realize that we are the deal breaker, and we need to take advantage of that we play a very big role in the big picture. Don't be afraid to speak up, be a great communicator. I've got a client that I've been in meetings with, and she will turn to me and go, "What do you think of that carpet?" And I'm like, "That's not a structural engineering question." She goes, "I know, I just want to know what you think of that carpet." And it's like, okay, good, here's my opinion. Also be active in your community, and that only can make our profession stronger. I sat on a board at my golf club, and we had a very difficult decision to make, and I came out and voiced my opinion, and somebody said, "Boy, we ought to have more engineers on our board, because we know how to look at a problem, analyze a problem, and come up with a solution." Be active in your profession. You already know that I've been very active in my profession, in our profession, and it's been very, very rewarding. And the thing that makes it most rewarding to me is what we're doing to help young professionals that are going to be coming up and taking over in the next few years. And then also remember that your clients do need your input to make them successful. They can make some really bad decisions if you don't help them. So that's important. Finally, I just wanted to talk about the vision of the future for structural engineering. In 2013, SEI wrote this document. It was about what's going to happen, what the structural engineering profession is going to look like in 25 years. I chaired the committee that updated this in 2019, and that document is readily available on the SEI webpage. You can see there's the link right there. And then, as I said before, we also took that and we've meeting with NCSEA, which is the Organization of State Associations, and the Coalition of Structural Engineers, which is the Organization of Structural Engineering Businesses. And we agreed to a vision together. It's a one-page document, but we're all pushing in the same direction now, which is really nice. I'm optimistic about the future of structural engineering, and there's a couple of reasons. Resilience and functional recovery. We're going to be putting pressure on better structural performance for new and existing buildings. Functional recovery, the concept is that we're looking at what a building does and deciding on a building occupancy use, if you will, whether how important that building is and whether we should do more to enhance the design for seismic and wind and everything else. There's always going to be a demand for new structures as the population continues to increase. And then there's other pressures, sustainability, economic, and societal reasons to try to reuse buildings. So those are all important to me, and I think that's why we can be optimistic, because I don't think any of those are going to change. And finally, that's the end. There's just some resources if anybody wanted to look at anything or send me an email or anything else. And my company webpage is there too. So that's the end. Thank you. If any more questions or questions I maybe can answer.